So my goal today is to work on something called molecular compounds, and then tomorrow we're going to focus on ionic compounds. So Riley, once you finish grabbing those notes here, then hopefully everybody will have them to work off of. Guys, can I ask one thing though? Print them off in advance, okay? Try not to print them off like at 10:10, because I got stuff I want to get to here, okay? Now, I don't mind giving you guys a few minutes here to kind of get organized, but this is really cutting it too late, hey? So, anyways, go do that quietly, and then once you get some notes, then continue following along. So, today we're going to talk about something called a molecular type of compound. Tomorrow we're going to talk about an ionic compound. And one of the best ways that I have found in order to try to organize things for kids so they can kind of keep track of what we're doing is I made a bit of a flow chart right. Oh, it's way further in the notes here. Right here. So I know this is like on a slide way in the future. But I found that this right here works well to help keep track of what we're going to do over the next little bit. Today, we're going to talk about compounds, and then we're going to learn how to name a certain branch of them, known as either the molecular or covalent ones. Okay, so we're going to start simple today. Then tomorrow, I'm going to teach you guys about a different type of compound called ionic compounds. And these guys, I actually break it up into 3 subcategories. But I don't want to get into that right this second because we're doing that tomorrow. But this basically, if you're wanting to make some notes here, this is what we're going to do today. We're going to focus on this kind of section in the flowchart. And then these 3 ionic ones, we'll do that tomorrow. Sound good? Sounds good. Yay! Okay, thanks. Okay, so let me go back to where I was here. You guys okay? Okay, so today when we talk about compounds, what I really need to focus on is your periodic table. So if you have it nearby, you're going to want to make some more notes on this. And if I can give some advice, put all sorts of stuff on this table here to help you when you write your next quizzes or your assignments. Don't have a blank copy. If I see a blank periodic table, I see a student who hasn't engaged the way they should. Okay, you should have lots of info on here. So I want to focus first on some terminology we learned like last week. The term metal and non-metal. That really is important when we talk about how to make a compound. Okay. Hopefully you guys will recall that all of our metals are over on this side of the periodic table on the left-hand side of this little staircase. These guys over here are all metals. And then our non-metals are the guys that are on this side, the right-hand side of the staircase. And there's a few exceptions. We call those the metalloids. But for the most part, ignore those. We're going to focus on metals and non-metals. Okay. Now, before I go further into that, I need to remind you guys, what is a compound? Well, the technical definition of a compound, do you want to take it? Give it a try. What's a compound? 2 or more elements. Okay. So if I take all of the things that the 3 of you said, let's put it better in a better definition. 2 or more elements combined in a specific ratio. And an example would be something like water. But why is water an example? What's water made out of? Yeah, H2O. Yeah, 2 hydrogens and 1 oxygen makes water. Or carbon dioxide, CO2. So as soon as we start taking more than one of the elements on the periodic table and putting them together, that's what makes a compound. Is that clear to everybody? Elements are just one item off of this table. Put 2 of them together, now you have a compound. Now there's 2 different ways we're going to learn about this. The first way, the molecular or covalent way, is where 2 different non-metals combine together. And you guys already know one of these, carbon dioxide. If you have a periodic table nearby, carbon is a nonmetal, and oxygen is also a nonmetal. And so when carbon and oxygen, both nonmetals, combine, we call that a covalent compound. So that's one type. We're going to focus on those today. 2 different non-metallic elements. And what they're going to do is they're going to share some of their electrons. And I'll explain that bit in a second. Tomorrow we're going to talk about ionic compounds. And the way ionic compounds work is that 1 metal off the left-hand side of the table and 1 non-metal on the right-hand side of the table, they join together. And a great example of this would be sodium chloride, NaCl. NaCl is salt. Okay? It involves sodium, which is a metal, and chlorine, which is a non-metal. And if you put 1 of each side together, it's still a compound, but it's a different type of compound. We call those ones ionic. Say that again? Yeah, basically what you're doing here, I'll even write some stuff out here. If you were to have, like, say, CO2 or H2O or CCl4, all of these guys right here, they're all non-metals. And so because of that, we call these things molecular compounds. Carbon and oxygen, both nonmetals. Hydrogen and oxygen, both nonmetals. Does that make sense? Tomorrow we're going to talk about how to deal with what you have what's called an ionic compound. And it's different, but it's similar in the way that you're still going to have more than one thing, like say NaCl. This is now going to be a metal and a nonmetal, where these guys right here are both nonmetals, both of the items in it. Okay. Now, in general, we're only going to learn about compounds that have two elements in them. Can you guys make sure you pay attention? Okay. But Tennille, your definition, I believe you said two or more elements that combine. It is theoretically possible to have two things, or three things, or four things, or more combined. But in general, in Science 9, we're normally going to have one of column A, one of column B, and we put them together in a compound. So that's my goal for the day. That being said, before I get to this, I actually want to focus a bit on elements first. Because before we can work our way up front to compounds, smaller than a compound is just a single one guy, an element. Does that make sense? Like, for example, sodium is a single one element. Chlorine is a single one element. Together, they make a compound. But before I get to the compounds, let's talk just about what they're like by themselves. So I believe that's my next slide. Oh, never mind. My next slide was actually just a visual of how matter works. Does that make sense? How elements would be like hydrogen or helium or nitrogen, but a compound would be HCl, NO2, CH4. You guys get the difference here between what makes something purely an element or combined to a compound? Okay. Okay, so what I have on this slide here is I got to talk first a bit, though, about what if we're not up to the level of compound? What if we're still just talking about an element? How does that change things? And I have another word I need you guys to know, and we're going to write some data on our table. The word is called an allotrope. Okay. An allotrope basically refers to when something is in an element, how many are there? Okay. I want to go back a second here to a previous slide. When I wrote out CH4, you see how there's that little 4 in the corner there? If you don't already know, that 4 basically means that there's 4 hydrogens. And this 2 right here means there's 2 oxygens. Does that make logical sense? But in HCl, how many chlorines are there? 1. We don't ever write the number 1. If there's only one of them, we don't write a number. Okay. Now, when they're in compounds and they're put together, if I give you N2O4, hopefully you know that now that there's 2 nitrogens and 4 oxygens. And if I give you NaCl, it means there's 1 sodium and 1 chlorine. We just didn't write a number. Okay. But that same logic still applies to elements. If we have an element just by itself, how many do they come in groups of? And that word we use is called an allotrope. Basically, it refers to, do they come in groups of 1, groups of 2, groups of 3, groups of 4? There's even some things that come in, like, say, groups of 8. And so when you're first learning about chemistry, you usually either need to memorize these or just write them down. And so I found that it's worth my time to have you guys grab your periodic table and write down some of the common allotropes. So here's the rules. Pretty much every metal is a single. Okay? If it's on the metal side of the table and it's by itself as an element, there's only one of them. For example, sodium. See this Na right here, sodium? I don't write a number next to it because sodium just comes in like ones. Okay? But there are some things where they come in like a 2-pack or a 4-pack. I give an analogy of, like, say you go to the grocery store and you want to buy soup. You could buy soup by the can in a group of 1, but you could also buy it in like a dozen, like in a 12-pack, like a case. Does that make sense? I had to buy my daughter a toothbrush the other day, and there was like single individual toothbrushes, but there was also like a 4-pack, which was like cheaper. If you can kind of think of that concept, there are some things, like say mercury. Mercury does not come by itself. For whatever reason, and this is well above Science 9, but for whatever reason, mercury comes in groups of 2. You'll never find as an atom a single mercury. It always has a twin. I heard you guys saying that earlier. So if you guys could, down here on mercury, I would highly recommend you put a little 2 next to it, just so that you know that mercury comes in groups of 2s. So metals are really easy, though. With that one exception of mercury, every single metal, if it's an element, you only get one of them. So those are nice. But the non-metals are very tricky. Many of the nonmetals are what we call diatomics because they always come in like a 2-pack. So I would really recommend write some of these ones down. Start up here in the top left-hand corner. Hydrogen doesn't come by itself. It always has a twin. So it comes in a 2-pack as an element. Nitrogen, oxygen, fluorine. I've missed one on here, by the way. Chlorine. Chlorine, by the way, comes in groups of 2. Chlorine, bromine, and iodide. They all come in a pack of 2 as well. I'm going to go to the back table here with the meter stick just to make sure this is clear. So I would write this down on your table here. This hydrogen comes in a 2-pack. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodide. There's kind of like a little corridor around the edge here. These guys here all also come in a 2-pack. Okay, you'll never find a single chlorine atom. Does that make sense? But if I give you cobalt, yeah, that you'd have one of them. Okay. Now, this is where it gets kind of weird. There are some things that have really strange numbers, like say sulfur, which is right here. Sulfur actually comes in a group of 8. We actually give a weird name to it. We call it a flower of sulfur, like Flower, like a grow outside in the ground flower. And I think the reason they call it a flower of sulfur is that each of the 8 sulfurs is like a petal. You know how like a flower has different petals on it? I think that's why they picked it as a flower. I've got a few more down here. Phosphorus comes in groups of 4s. Arsenic comes in groups of 4s. Carbon is actually really weird when I have a slide next to it. Carbon can come in many different groups. It can come in a group of 1, 2, 4, I think 20 as well. And I'm going to show you that on my next slide, that carbon actually has a lot of different allotropes. And I think you guys actually know a little bit about this. You just didn't realize you knew it yet. The last one I need you to know about is that oxygen normally comes in a group of 2, but oxygen can actually come in a group of 3. Has anybody ever heard of ozone before? Who's heard of ozone? Anybody? Where do we find ozone? Yeah, it's in the atmosphere. You ever heard of the ozone layer? Okay, well, the ozone layer is like high up in our atmosphere. It filters out ultraviolet rays from the sun so that we don't get skin cancer. Now, it doesn't do it perfectly, so we still need to wear sunscreen. But if you ever heard of it, it's called the ozone layer. Well, ozone is when oxygen is in a group of 3 rather than a group of 2. I want to spend this next slide, though, talking about carbon, because carbon is actually quite unique. Carbon has a lot of different allotropes. I want to show you 3 different ones that I know you guys are aware of. You good? Okay, here's one right here. This is like just generic soot. Like you burn something in your fireplace, and when you're done, you have ashes left over. This would be carbon in just a group of 1. And if it's in a group of 1, it looks something like this. Just basic ash. Now, if you guys didn't know this, though, when you're working with your pencils, we don't actually put lead in our pencils anymore. Lead's poisonous. We use graphite. Graphite is actually carbon. Now, I forget which allotrope it is, so don't write this one down. But I believe it's like carbon in a group of 4 or carbon in a group of 6 or something like that. So if you had C4, you might have graphite. But I don't think it's C4 because C4 is used for like explosives, and that's like a different thing entirely, though. So diamonds are actually also made out of carbon, and this is like carbon 20. Okay. Now, I'm not sure on my numbers, so please don't quote me on this. But if you get the concept here, the different number in the corner here makes it a completely different compound because a diamond is so much more valuable than ashes. You know what I mean? But it's all about the allotrope. If it comes in a specific grouping, it changes its composition a little bit, which is kind of cool. So I just need for you guys to be aware of these groupings as the numbers we put in the corner, because that tells you how many of them come in a pack, basically. So most things come in a group of 1. When I go to the store and I buy stuff, I usually buy just one of them, right? But sometimes I buy a 2-pack of something, or a 6-pack, or a 3-pack, right? Well, chemistry works the same way. Does that make sense? Now, I use that as my intro to compounds because that same concept applies, though, but now when we talk about compounds, we have to take these elements and put them together. So, for example, if I give you NaCl, which is a compound, it means that we have 1 sodium and 1 chlorine. If there's ever 1s, we don't bother writing the number 1. You guys do a little bit of algebra and math. You know how, like, if I wrote you the equation x plus 2 equals 4, how many x's are we talking about? Oh, sorry, you're solving it for me. What I'm asking is, there's one x written right here. Does that make sense? Whereas if I gave you 2x plus 2 equals 4, there's a 2 in front. So if I ever tell you that there's x minus 2 equals 7, do you guys get that there's like, this implies that there's one of them? We just don't bother writing the number 1. Yeah, we're lazy, right? Well, that same concept applies here. If I give you CaCO3, this is a compound. I know it's a compound because there's 3 elements put together. That's okay, we can work with that. This means that there is 1 calcium, we just don't write the 1. There's 1 carbon, we don't write the 1. But as soon as you see the 3 after oxygen, it means there's 3 oxygens. Is that pretty straightforward? So Al2S3 involves 2 of these and 3 of these. Now, a while ago, I taught you guys about some different scientists who had some contributions. And one of them who I'd like you to know, his name was Anton Lavoisier. And one of his biggest contributions is that he realized that we need to talk about the same thing. Okay? We have to have one name for one chemical. Okay? And the English language is notorious for this. For example, if I were to ask you what Chase is wearing on his head, some of you might say that he's wearing a hat. My grandfather would say he's wearing a cap. I don't know that anyone ever says cap anymore. But we have 2 words for the exact same thing. Does that make sense? We can't have that in chemistry. If we're going to talk about that compound right there, we all have to use the same word. Someone can't call this a cat, and then someone else call it a kitten, and someone else call it a something else, right? Like, we have to all use one word for one item. Does that make sense? I don't have a really good example, but... Exactly. Yeah, they all sound the same way. Yeah. It would be like calling this a desk or a table. Which one is it? Is it a desk or a table? Well, it doesn't really matter, but in chemistry it really, really matters because I can't have somebody calling this sodium chloride and somebody else calling that blah, blah, blah. Right? Like, we have to have one name for it. Okay, anyways, here's the point I want to make. What I'm going to teach you guys for the next little while, bring it back in, focus, is called chemical formulas. We're going to learn the names for these chemical formulas and the rules that we use. If this ever comes up, they're called the IUPAC rules. Okay, and this is like the international system, so that if you went to school in China or Russia or Argentina or wherever, in theory, everyone should be calling these the same things. What did I screw up here? Oh, but on your notes, yeah. For some reason, it formats them weird when I download them to PDFs. Yeah. You guys can still follow though, right? Yeah. I know. I don't know why it does that. Okay. Anyways, let me make sure that we're kind of clear on what we're going for here. Right here, what we're going to do is we're going to take 2 elements. This sodium and this chlorine would be elements, but when we put them together, this is now a compound. Does that make sense? This hydrogen and this oxygen are individually elements, but put them together, we now have a compound. My goal today is to teach you how to write the formulas and how to name them. We would call this thing NaCl because there's 1 sodium and 1 chlorine. This one right here, we would call it H2O, and we'd call it H2O because hopefully it's obvious. There's 2 hydrogens for every 1 oxygen. So the writing the formulas is not usually too bad because you literally just look at what's there and say, well, here's what we got. But we all have to call it the same thing. You guys all know how to name this guy right here, don't you? H2O is, yeah, but it has to be consistent. I can't call it water and have you call it something else. That gets confusing. So, okay, let me skip ahead to, why don't I skip ahead to this slide right here now? Because I kind of talked about the other slides here. So, today when we learn how to name stuff, we're only going to name stuff that involves 2 nonmetals. Okay? So in terms of your periodic table, you know how you have the whole thing here? Today, and only today, we're basically only going to look over here, just to kind of narrow it down at first. Okay? Tomorrow, we'll eventually use elements that are on this side over here, but for right now, we're only going to work in the nonmetal section. It makes it easier. So here's how this works. The guys in the nonmetal section, they're going to share their electrons. Okay? I have an analogy I like to use when I talk about covalent bonds. You guys know how when we go to the cafeteria and you want to buy a special costs $6. Okay. Now, let's say that I only have $4 and you only have $2. Neither of us has quite enough. But if we pool our resources and share, then 4 plus 2 means we can both get a special. We can get a special because 4 plus 2 gets you 6. But you have to share. Yeah. So that's the key word right here about covalent bonds, is that when you bond them together, each element is going to share some of their electrons. Going to share their electrons, and that's what makes a bond form. I'd like to show you carbon dioxide if I could. Okay. The way carbon dioxide works is that you have one carbon and two oxygens. So I'm just going to write them off on each side just because I know where this is going to lead to. Now, the way this one works, it's all about what are called the valence electrons. And if I haven't used that word well enough in the past, let me review it now. A valence electron is the electron in the last energy level. A valence electron are the electrons in the last energy level. So I want to look at carbon. I'm just going to make like a pretend periodic table real quick. Here's like kind of the basics of it. Let's see, we have like this, and there's like the gap here, and then it goes like this, and then there's hydrogen up here, helium right there. Okay, so I know I'm not the greatest artist, but here's a rough periodic table. Okay, carbon is right about here. And we've learned in the past that carbon is number 6. So what does that mean? If carbon is number 6, it has 6 protons. And in its element form, it would also have 6 electrons as an atom. But I want to focus on those electrons. Okay, in the first row, I'm going to have to go to the back, I think, actually. I'll have to teach from back here. Carbon, way back here, see how carbon is right here? It is in 2 energy levels. This is the first energy level, but carbon is in row number 2. So it needs 2 energy levels. Does that make sense? My question for you then is, how many electrons are in that energy level? Well, there'd be 1, 2, 3, 4 electrons in its second energy level. 2 of them are in the first level, and then 1, 2, 3, 4 are in the second level. So carbon has 4 valence electrons is what we'd say. By that logic, how many would oxygen have? 6, yeah. Because oxygen is number 8, which means it has 8 protons. 2 of the electrons are in energy level 1. Don't care about those. But then 1, 2, 3, 4, 5, 6 more electrons are in level number 2. I'm going to come back to that thought. So let me write this down here. I'm going to do some more drawing here as well. Oxygen should have 8 protons and 8 electrons. And sometimes we would draw them kind of like this. I'm going to need a new slide here. We would say that here's your nucleus, and then there's the first level. And there's 1, 2 electrons in the first level. And then in the next level, then let's do carbon. Carbon would then need 1, 2, 3, 4 electrons. And hopefully you guys can see that this is now carbon because there are 1, 2, 3, 4, 5, 6 electrons. But only 4 of them count. So I'm going to say carbon has 4 electrons here. Yes? Basically, the electrons in the first level are the ones that hydrogen and helium would have had. Does that make sense? Let me try drawing another one here. If I drew oxygen, here's how oxygen would look. Here's a nucleus. You'd have energy level 1. Now, oxygen should have 8 electrons. 2 of them go in the first level. Then we start the next level. Okay, well, I need 8. So then this would be number 3, number 4, number 5, number 6, number 7, number 8. How many valence electrons does oxygen have? 6. Because 2 of them are in the first level. We don't count those ones. There's 6 in the next level. Now, what's going to happen here, if I can go back in my drawing here, is that we sometimes draw these with little dots. And I would say that oxygen has 1, 2, 3, 4, 5, 6 dots. Carbon has 4 dots. And oxygen here has 6 dots. Those are how many electrons you have. I'm just going to draw them. Well, what ends up happening when you form a bond is that they have to share their electrons. Okay, now I'm kind of jumping a little bit beyond what we're going to do in this course. So if this next section here does not make sense, please don't freak out. But I'm hoping that this will help explain a little bit. What happens when they share their electrons is that these electrons right here, see how there's like 2 free ones there? They share them. They collectively pool their resources. This guy brings 1 electron to the table. Oh, I guess I have 14 minutes to finish. Okay, these guys share their electrons, and this guy brings 1, this guy brings 1, and collectively they form themselves a bond. Does that make sense? And then this guy over here, this carbon and this oxygen, here they say, well, I've got an electron, you've got an electron. Why don't we work together, and I'll bring 1, and you bring 1, and we'll share what we have. That same analogy works for going to buy something in Blair's Kitchen. I have $3, you have $3. We don't each have enough, but if we pool our resources, 3 plus 3 eventually gets us to 6. That same thing is happening here. Carbon has a valence electron, oxygen has a valence electron, and they pool them together, and that's what makes a bond. Okay. Now, if that didn't fully make sense, please don't stress out. That's not really the point of today's lesson. But what I just need you guys to know is this word. They share their electrons. Okay. If you can accept that, we're good. So let me move on here. Here's how we name them then. It's a very simple naming scheme. Okay. When you name something, it follows these rules. Okay. First, you use a prefix. Then you use the first element. Then you use a second prefix. Then you use the second element, and you change it to "ide." And that sounds so complicated that you're probably thinking, wow. But you guys already know this. I want to show you a compound you guys are already aware of. I'll do that one in a second if you'd like, but let's do this one here first. CO2. You guys probably already know this one as carbon dioxide. Watch how that fits here. We actually don't use a prefix if there's only one of them. Just like when I've mentioned before, if there's only one of something, we sometimes skip the prefix because there's only one carbon. So I'm not going to write a prefix. And then I'm going to say first element. Well, the first one was carbon. So no prefix required. I wrote the first element. Okay. Then I wrote a prefix, though. Well, we call it carbon dioxide. Why do you think the di in the word came from? Because there's 2 of them. Does that make sense? Sorry, that was meant to be rhetorical. So because there's 2 of them, this 2 right here means we call it a dioxide. And then when we change the last one right here, rather than calling it oxygen, because normally you'd call it oxygen, we change the ending to oxide, and that's where the word comes from. So CO2 is carbon dioxide because there's 2. Okay, let me try another one here. If I were to give you N2O. Well, be more careful here. This one actually requires a prefix. See how there's 2 nitrogens, though? We're going to call it di-nitrogen because there's 2 nitrogens. And then you just need to know the prefixes. So they're on the next slide somewhere, but if you only have one of something, we do use 1 if it's the second word. So because there's 1 oxygen, we're going to call it a monoxide. So this is dinitrogen monoxide. Anybody ever heard of carbon monoxide? Carbon monoxide, which is like you get that in like a fireplace that's not burning properly, would be 1 carbon. Because I didn't put a word in front of it, there's 1. And then because I said it's monooxide, then you just need 1 oxygen. That's carbon monoxide. So it's actually a really easy naming scheme. You just have to get kind of how it works. So I've got the prefix list right here. So it just means you need to know all of the different prefixes. If you have 1 of something, call it mono. 2 of something is di. 3 of something is tri, etc. So here's the advice I would give kids. Again, while you got your periodic tables out, write these down somewhere. Because then you don't have to memorize them, right? Okay, I've got 10 minutes to finish here before my computer auto shuts down on me. So what some really smart kid pointed out to me one day is they use the little numbers across the top here. So there's like a 1, 2, 3, 4, 5 along the top there. They just wrote the prefixes right above those. So under 1, they wrote mono. 2, they wrote di. 3, they wrote tri. I thought that was actually really clever. Okay. But you definitely want to write these down somewhere. Come on. Oh, they just threw it in there. Thanks. Was that? Yeah, some of these ones are Latin origins, I believe. Yeah. And I mean, we use some of these prefixes in other examples. Like, for example, a tricycle has 3 wheels to it. If you ever buy a Tetra pack of something, that's usually because there's 4 of them, perhaps. A pentagon has 5 sides. A hexagon has 5 sides. Right? Now, not all of them are perfect, but yeah, I guess an octagon has 8 sides. So a lot of these you should probably recognize from other places, right? So, so I'm going to give you some more examples here. So you don't even have to read these ones out, just follow along. We call this one carbon dioxide because there's 1 carbon. If ever the first thing has 1, we just don't bother writing mono. So this is carbon dioxide because there's 2 oxygens. This one is dinitrogen monooxide because there's 2 and 1. Dinitrogen trioxide because there's 2 and 3. Does that kind of make sense? If the first one, though, only has 1, we don't write mono. So you might notice that this one right here has 1 phosphorus and then 5 fluorines. We don't call it a mono phosphorus if the first one starts with 1. That's the only rule we have. So one of the things I need you guys to be able to do then is if I either give you the formula, you can write out the name, or if I give you the name, you can write out the formula. So let's try an example slide here. See whether you guys have picked up on how this works. I want you guys to name CO2. We've already done that, right? 1 carbon, 2 oxygens, call it a dioxide. Is that easy enough? Well, again, 1 carbon, but now there's 1 oxygen, call it a monoxide. Okay, what about the next one here? Good. So this one is a trinitrogen. The next part's kind of tricky to know how to put it together properly. What's 6 though? Hexa. And then you'd call this a hydride. Yeah, you take hydrogen and change it to hydride. Sometimes you just need to hear how we make them work. So hydrogen becomes hydride. So this is trinitrogen hexahydride. Yeah, and this is why Lavoisier's idea is so important, is that now we're all using the same words, right? And so it does sound very technical, but once I explain it to you, hopefully you're able to follow along. I'm glad. Well, let's try the next one here. If I don't give you the formulas, but I give you names, can you write it? Well, all you need to know now is your symbols. Silicon is Si. Yeah, it's actually not writing. I still have 6 minutes left before it boots me out. There we go. Okay, that was weird. So silicon is Si. I'll have to write it over here. How many silicons do I need? Just 1, because there's no prefix in front of it. But then there's a tetrafluoride. Fluoride is fluorine, and we want 4 of them then. Okay, well here we need a tetraphosphorus. Phosphorus is letter P, so we need 4 of them. And then deca means we need 10 of oxide, 10 oxygens. Or on this one here, dinitrogen, so nitrogen twice. Oxide, we need 1 of, but don't write the 1, right? Just skip the 1. What do you guys think? Is this something you could do? I feel like when I'm explaining this to students at first, some kids, they go, oh, this is easy, I got this. It still doesn't hurt to practice a little bit, though. Oh, because you may just want to do 10 of these or 5 of these just to get the hang of it. But once you're good at it, it's a very classic, clean, simple naming system. All you need to do is know these prefixes and just know what your elements are. Oh, wait, let me move on. The last thing I need you guys to know about before my computer auto restarts is some properties of molecular compounds. I want to describe some of them for you. One of them is carbon dioxide. Well, carbon dioxide is a gas. Other ones that are molecular compounds would be something like, say, N2O4. That was dinitrogen tetraoxide, also a gas. One of them that we do, water, H2O, it's actually molecular. Okay. It's actually a liquid, but it turns into a gas fairly easily. So one thing that I need to know about most of these is they all have a low melting point. And by low melting point, I mean that most of these things are either a liquid or a gas. Very few covalently, molecularly bonded things are solids because they almost all melt very easily. Right? Carbon dioxide is a gas. It is not just melted, it's also boiled. Does that make sense? So now, if they were to form a crystal, another property I want you to know is that they're very, very weak. For example, water is actually a good example of a molecular compound. Water is two nonmetals. But water, when it forms a crystal like snowflakes, it's actually really easy to break, right? We get frost on our windshields in the wintertime. Now, I know it's a pain, but it's actually really easy to scrape the frost off, right? As opposed to like ionic compounds would be really, really, really hard to scrub that away. So they actually have very, very weak crystals. Okay. I actually have a slide here showing you a couple of molecular compounds here. Carbon dioxide and water are some that you guys should be able to do. Sugar and rubbing alcohol are a little bit more advanced because they have 3 parts to their formulas, and we don't really go that far yet. But you'll notice that all of these involve nonmetals. And as a general rule, all of these things have relatively low melting points. This is in the negatives, but these guys right here are between, like, say, 0 and 100. Those are low. Okay, a high melting point would be like 5,000 degrees Celsius. Okay, that'd be a high number. So these things are usually either gas or liquid. The only one that's really not is sugar. But even then, sugar, you can actually melt sugar fairly reasonably, which is why we make like candies out of melted sugars. So, okay, the last property I need you to know is that molecular substances do not conduct electricity. Okay. And the theory behind this is a little harder for me to explain until we learn a few more things. But the basic idea is that because these things are all nonmetals, nonmetals are typically negatively charged anions. And if you only ever have negatively charged anions, they don't conduct. Tomorrow, though, when we learn about ionic compounds are going to use negative anions and positive cations. And when you have some positive and some negative, then they do conduct. But these guys right here, they don't conduct. So if you can just memorize that they don't conduct electricity, that's good enough. If you want me to try to explain better, I can do that tomorrow once we talk about the ionic ones, because they're a contrast. Those do conduct. So, and then here's kind of my last two slides, right? Yeah, last 2 slides. 1 minute. Got to go fast. Okay. Okay. Ionic bonds are what we're going to talk about tomorrow. Ionic bonds don't share their electrons. They actually give them away. Tomorrow we're going to talk about a guy who's going to have a spare electron and someone who needs an electron, and they're going to transfer theirs. But today what we talked about is how these guys right here, they're going to share their electrons together. So we've really only done about half the lesson so far. We're going to pick this up again tomorrow. The other slide I have right here is that there are some compounds that rather than calling them their formal names, we actually give them like nicknames. For example, water. Water should actually be called dihydrogen monoxide, but we never call it that. We just call it water. So I've got a list of compounds right here that have a formal name, and then they have like a common name. You should know some of the common names, like say water or methane. Okay, that's it. I've got to pause this because my video is going to stop real quick here.